Hello everyone, today we're going to be talking about L'Hopital's rule, and today's tutorial is going to be pretty short. It's a pretty simple rule, but one that's really useful. Right off the bat, for our Francophone viewers, it's not the rule about the hospital. It's named for Guillaume de L'Hopital, French guy from the 17th century. And so to start, we're going to recall back when we had trig limits. I told you in the first video, hey, you got to take my word for it. This is one, we'll talk about it later. Well, today we're going to talk about where that comes from. It's a natural consequence of L'Hopital's rule. And so L'Hopital's rule is for when we deal with an indeterminate form. We have right here the actual definition of it, so take a look. If you have two functions in a limit, and it's rational, and both of those functions are differentiable, and you get an indeterminate form. Okay, let's talk about what an indeterminate form is. The most common are going to be when you have infinity over infinity, or when you have 0 over 0. Indeterminate because we can't determine the value of those without more information or without more context, so we call them indeterminate. There are other indeterminate forms like 0 to the 0 power or 1 to the infinity, things like that. So there are lots of other indeterminate forms, but these ones in AP seem to pop up the most, as well as in IB. Okay, so here's our rule. If we know that both of those are differentiable, we know how to take a derivative of them, and we get an indeterminate form, it has to produce an indeterminate form. Sometimes people apply the rule when there's no indeterminate form. That's bad. Don't do that. Okay? When you have that indeterminate form, though, you can independently take the derivative. It's not a quotient rule. Independently, take the derivative of the numerator and denominator, and that's an equivalence expression. Okay, so let's apply that up to this example real quick. First of all, let's verify that it is an indeterminate form, because you have to satisfy the hypothesis first. So let's see. If I plug in 0 there, and 0 there, I get sine of 0 over 0, which is in fact 0 over 0. Okay, so it is an indeterminate form, which indicates to us that L'Hopital's rule does apply. So what we're going to do then is we need to take derivatives of numerator and denominator independently. And here's what it looks like. We take a derivative of sine, that turns into cosine. Take a derivative of x, that turns into 1. And note, it's still a limit. So we have limit as x, or excuse me, in our case it's not x, it is theta. So as theta approaches 0 of cosine of x over 1. So we're going to try the substitution again. Plug in a 0, that's cosine of 0 over 1, which is 1. Okay, so that verifies our identity that we learned when we were talking about trig limits. Okay, let's look at two other cases, and that's going to be a wrap for today. Okay, the other two examples that we have are down here. The first one is a word of caution. Okay, be careful, because this is an indeterminate form. If you plug in a 3, and you plug in a 3, then yeah, that will absolutely be 0 over 0, and you can use L'Hopital's rule. Remember, you can also, on an example like this one, you can factor it and cancel. Because it is indeterminate, let's try L'Hopital's rule and see if it works, and then we'll also show it with factoring and canceling, because we want to verify that we're getting the same thing. Okay, so L'Hopital's rule is why this turns into a 2x, that turns into a 1, and then we get limit as x approaches 3 of 2x over 1. When you plug in the 3, you get 6. Let's verify that with our old school analytic method where we factored. So that would look like limit as x approaches 3 of x plus 3 times the quantity x minus 3 over x minus 3. And what do we have? We get to cancel, we get to plug in a 3, and 3 plus 3 is in fact 6. Okay, so that should provide us a little bit of comfort that this rule works. We use an analytic, trusty technique, that gets 6. We use L'Hopital's rule, we get 6. Let's do one more, and that's going to be it. Okay, with this one, let's double check. If I plug in infinity, e to an infinite power is infinitely large. An infinitely large number squared is still infinitely large, so that is infinity over infinity, so let's apply the rule. Limit as x approaches infinity of, derivative of that is e to the x, derivative down here is 2x. Now we're going to try plugging in infinity. Not legal, but we're going to do it anyway. Okay, plug in the infinity. Those are both still infinitely large though, so what are we going to do? That's an indeterminate form. Well, the only thing we can do is apply the rule again. Okay, so let's try it. Limit as x approaches infinity. Okay, still its own derivative. This now turns into a 2. When we plug in infinity, it looks like e to something infinitely big over 2. So the only trick to this now is if you take e to infinity, that's infinitely large. When you divide something infinitely large, how big is it? Still infinitely large. Okay, so this is infinite. This diverges. Okay, that's our intro tutorial on L'Hopital's rule. Hope it makes sense. Hope you enjoyed, and we'll see you next time.